Hello everyone, it's Benny, and in this video, we're going to be implementing shadow mapping in a 3D engine to show you a practical implementation of the technique. Now, in the last video, we went ahead and added all the engine features that we're going to need to actually implement shadow mapping. So if you haven't already, you can go watch that video, or if you don't care about all that, you can go into the finished code repository, go into the commit history, and download the commit right before this video's code is uploaded. And that way, you don't have to bother with that. So, either way, let's dive in, and let's get started. So, if we're going to add shadow mapping, the first thing we need, surprisingly enough, is a shadow map. So, what I'm going to do is, in my rendering engine, I'm going to set a new texture. I'm going to set a texture called shadow map. And this will be our shadow map, of course. And for the parameter, it's going to look a lot like mTempTarget, so I'm just going to copy and paste that, and we'll modify it as needed. So the parameters. We need some width and height. I'm going to hardcode 1024 by 1024 now. Later on, I'm going to add some way to specify this, but at least for now, I'm going to just hardcode it 1024 by 1024. Why that particular resolution? That's generally a pretty good upper bound. Occasionally, you need to go over it, but if you do, there's a pretty good chance you've just missed something, so that's generally a reasonable upper bound for shadow map size. Texture 2D is good, and we don't want to pass anything by default. Texture 2D, that's fine. Nearest filtering, that's good, we want that. In fact, make sure it's on nearest filtering. For the internal format. Now, if you remember from when we talked about how shadow mapping worked, what we use the shadow map for is to look up how far the pixels in the shadow map are from the camera. So, we don't actually need color information. We just need the depth component. And specifically, I'm going to specify the format as depth component 16 for a 16-bit depth component. Because usually that's going to be good enough. Sometimes it's not, but usually they'll be fine. And for the format we pass in, it doesn't matter too much since we're passing in nothing, but for good practice, we should specify it as depth component. Now, do we need to clamp? In this case, yes, I do want to clamp. I'm going to set that to true. And the reason I'm going to set it to true is because if we're sampling at some point outside of the shadow map, then, we don't want to sample, shadow, we don't wrap around and sample a shadow from a completely different part of the scene. So, yeah, we do want to clamp. If we're reading outside the shadow map, then just don't return anything. And finally, the attachment is going to be GL depth attachment. Because, of course, we're rendering depth information, so we want to, of course, send in depth information. And that's good. That should set up the shadow map. One more thing, though, is in my main.cpp, I'm going to comment out the lines of code for the point and spotlight. And the reason I'm going to do that is just to simplify things. This way we only have one shadow casting light to start out with, and once we have things working for the direction light, then we'll start going in and working with the other types of lights. So, let's run to make sure I didn't break anything. And, good. So, everything's working out. So, now that we actually have our shadow map, we need to modify our lighting system so that our lights have information about how to cast shadows. And just to make this a bit easier, I'm going to create a new class for this. I'm going to call it shadow info. Info, yeah. And this is just going to store all the information a light needs to cast shadows. Why am I wrapping it in a class and not just putting it directly in the base light? You'll see in a moment. So, I'm going to need public, protected, and private parts, just like any other C++ class. And for now, there's only one piece of information I care about for shadow, and that's a matrix 4F M projection. And this is the projection matrix that's used for the camera when we're actually, rendering the shadow map. And that's really all we need right now. The position of the light and stuff's already stored in the light, so all we need is, well, the projection of the camera we're going to use to render it. So I'm going to create a constructor for it. And it's going to take in matrix 4F reference, sure, projection, and we're going to use initialization list, set in projection to the projection. You don't have to use an initialization list for that. You can just, do the usual in projection equals projection in the constructor. I'm just doing it this way because, I don't know, just because, really. And finally, I want a getter for that. So, inline matrix 4F get projection. Just going to return the projection. There, great. So, why on earth have I put this in an entirely separate class rather than just making it part of the base light? And here's why. My base light is going to store a shadow info pointer called imShadowInfo. And this gives us a really nice, easy way to specify whether or not a light should cast shadows or not. Because I'm going to start with imShadowInfo initialized to 0. In other words, it's null. So if it is null, then we can know, hey, this light isn't supposed to cast shadows. So we can just skip the shadow casting phase and just draw the light. Otherwise, we can read the shadow info and generate the shadows like normal. So yeah, it's just a nice way to do that without having to have an entirely separate Boolean flag for it. So, yeah, not that it particularly matters, it's just, just a coding convenience thing. So, like with my shader, I'm going to have an inline shadow info pointer called getShadowInfo. And it's going to do exactly the same thing. It's going to return the shadow info. Just basic getter, nothing special here. And other than that, oh yeah, I do want a setShadowInfo function. So, in fact, since I don't want anything outside the light class to set these, I'm going to go ahead and make these protected. And great, so yeah, I think that's all I want to add to the lighting header, so let's just go ahead and implement that in the lighting. So, right here, right below where I've implemented setShader, I'm going to implement setShadowInfo, because it's going to be very, very similar. If there already is some shadow info, wait, what? Oh, I wanted to take in a shadow info pointer, not a shader pointer. So, yeah, shadow info pointer, I'll call it shadow info, there. And I'm going to mirror that down here. Great. So, if we do have imShadowInfo set to something already, then we're going to need to delete the shadow info. So, delete that. And then after that, we can assign it. So great. And of course, in the destructor, same sort of thing. If I did that backwards, didn't I? Okay. Well, that's okay. I can just be a bit creative with this. I can undo all that until it's back to shaders, and then copy and paste that there. And now this can be shadow info. There, much better. And in the destructor of the base light, just delete it. Great, cool. We have shadow info in our lights. Now let's actually use it. So here's what I'm going to do. I'm going to have a shadow info pointer in my direction light. I'm going to call it shadow info, initialize it to new shadow info. Actually, I don't even think I need to do anything special there, but I'll do it like this anyways. I'm going to have a matrix 4F. And I'm going to knit an orthographic matrix for the direction light. The reason it's orthographic is because, remember, a direction light is supposed to simulate a sort of light coming from infinitely far away. Light just sort of where all the light rays are parallel. And in an orthographic projection, well, no distortion of that kind is emulated. Everything is sort of parallel like that. Yeah. And as for size, right now I'm just going to hardcode something. I'm going to hardcode -40, 40, -40, 40, and -40, 40. Again, I'm going to add some way to specify that later. Right now I just want to get something working. So, there. Actually, I think I just pass it straight in, so setShadowInfo, which is nice. So there, great. And with that, I should be able to build. Not doing anything with the shadow info yet, but I should be able to build. And I'll run just to make sure I haven't broken anything with that. So great! We're running, we have a shadow map stored somewhere in memory, our directional light has information about how to render to the shadow map. You know what's coming next, folks. We're actually going to render to the shadow map. So, it's time to change the render function. The first thing I'm going to do is I'm going to remove this additive blending enable and disable code into the loop here. Why am I going to do that? Well, because we're not just rendering lights in our sort of, lighting loop anymore. We're also going to be generating and using shadows. So, yeah, we don't want to additively blend our shadow maps, we want to actually draw them. So, yeah, that's why we're doing all that. And with that, what we can do is we can start implementing shadows. First thing we want is to get the shadow info of the light, so shadow info, call it sure, shadow info, and that's going to be mlights dot, mlights of I, dot, I could have sworn that, okay, I guess it's just not going to do it. So dot get shadow info. And, okay, it is a pointer, so I want to do it like that. There. Don't know why IntelliSense was failing me there, but yeah, we want to get the shadow info. And here's what we're going to do. If shadow info, and this will be true, if it's not null. So if we're in here, then the light has some shadow info, meaning we want the light to cast shadows. And we'll do all the shadowing map generation stuff inside this if statement. Otherwise, what we want to do is we want to get rid of whatever's in our shadow map. So, and in fact, we're going to want to do that anyways, because we don't want to render more on top of an existing shadow map. We want to start fresh. So what I'm going to do right here at the top, I'm going to say get texture shadow map. And what we're going to do is we're going to bind that as the render target. And then, of course, at the end here, we're going to bind the window as a render target so that we actually draw everything, with the window as a render target at the end. But right here, we're going to bind the shadow map as a render target. And the first thing we're going to do, GL clear GL depth buffer bit. So there. That's what we're doing. Every time through this loop, we're going to clear whatever's in the shadow map. And then if there is a shadow to be cast, we're going to, render it in here and create the new shadow map. Otherwise, we're just going to use the blank shadow map to draw the scene with no shadows. So great! So how do we actually generate the shadow map? Well, if you remember from the video where I talked about how shadow mapping works, the way you generate a shadow map is you place the camera where the light is, and then you render the scene. So that's exactly what we're going to do. We're going to take advantage of the alt camera, so alt camera, and we're going to set the projection of this. Now, I actually don't have a function for this for some reason, so what I'm going to do is I'm going to go to camera, and I'm going to add a function just to set the projection. It's going to be very, very simple. It's going to be, I'm even going to inline it, inline void, set projection. It's going to take matrix 4f projection. Should probably make it a constant reference. Much better. And it's going to set projection to projection. Very simple, basic setter that you've probably seen a million times. Anyways, back to rendering engine. We're going to set the projection to whatever projection is stored in the shadow info. So shadow info, get projection. There. And other than that, we're going to place the camera at the position of the light. So, in fact, just to make life easier, I'm going to move the active light thing up to the top. So yeah, there. And alt cameras, I'm going to get the transform and set the position to the same position that our active light is at. So active light get transform dot get position. So cool, that'll set it to the position that the, active light is at. One thing you want to be careful of here, which I actually just screwed up right now, is you don't just want to get the position. You actually want to get the transformed position. And you gotta remember, the alt camera isn't in the scene graph, so, you gotta take into account all the different transforms that the scene graph might put in there. So there. And you also want to set the rotation in the same way. So we're going to set the rotation of the alt camera to the ActiveLight.getTransformed rotation. And there, that should set the camera all up for rendering the shadow map. So at this point, what we should be able to do is get a camera pointer, a temporary camera pointer, and set that to whatever the main camera is. Then set the main camera to the alt camera for rendering the shadow map, and at the end, of course, we're going to set the main camera back to temp. And yeah, at this point, I think we can just render it. So object. Oh right, object, not objects. Render all, and we're going to take in a certain shader and this. But what shader are we going to use? Well, we're going to need a special shader for generating shadow maps. So I'm going to have something in here, a shader pointer. I'm going to call mShadowMapShader. I'll initialize it in a moment, but yeah, that's what we're going to use to generate the shadow map. And up here, I'm going to initialize it to a new shader, and I'll call the shader Shadow Map Generator. And great, that should build. It's not going to run because we haven't written that shader yet, but oh, I've screwed something up apparently. Shadow info get projection. Did I call it something different? Shadow info. Oh, it's probably dot get projection. So, sorry about that. Wait, that doesn't make sense. Wait, what? Oh, I know why. Alt camera is a pointer. So yeah, I want to use arrow for that. Much better. Now it should build. It's not going to run, but it should build. Great. So now let's write that shadow map generator shader. So in 3D Engine CPP to res to shaders, you're going to want to create shadowmapgenerator.fs and shadowmapgenerator.vs. I went ahead and did that off screen just to save some time. And let's go ahead and fill these out. I'm going to sort of model them off of, well, the ambient shader. So I'm going to copy forward ambient. I'm going to paste it in here. Forward ambient.vs, well, just copy lighting.vsh and paste that in here. And there, we're just going to delete all the stuff that we don't need. And of course, the version is 120. So, we don't need any sampling stuff in here, so I can get rid of that. Now, we only care about the position in this, so I can get rid of all that. And that means we're not going to need to pass out any texture coordinates or world positions, anything like that, so we can get rid of that. We're not going to need the model matrix either, because we're not doing lighting, so we can get rid of that. So this just leaves position and the MVP, which are the only variables we should need here. And all we should need to do is set the position to MVP times the vec4 position. So great! That's our generator vertex shader. Fragment shader, not going to need any varying variables at all. In fact, we can just get rid of everything except for the frag color thing. Now here's the thing. Since we're only rendering to depth texture here, our frag color really shouldn't even be used. So this shouldn't be used in basic shadow map generation. But just in case something screws up, just to make it a little bit more fail-safe, I'm going to make a vec4. And I'm going to make a vec4 of, well, the depth. And how do you do that? What you can do is you can use gl_fragcoord.z. And this is just an OpenGL variable that gives you access to the depth. So there, I'm going to make a vec4 of that. And great, so that should be all we need in our special shadow map generation shader. So I should be able to build, should be able to run, not going to see anything different because we're not using the shadow map, but it should be generating it. So we're generating a shadow map. So that's great. We can't see it, but we're generating it. All we have to do now is change our active light shader, or, well, our lighting shaders, and then we should be good to go, pretty much. We should be able to have shadows. However, there is one thing that's going to come up that I just want to go ahead and take care of right now. And that is, in order to access the shadow map, to get the proper position in the shadow map, we're going to need, well, this right here. We're going to need this transform position from the camera's MVP. So, in order to make this possible, I'm going to make a matrix. Going to be called mLight matrix, and it's going to be accessible from the shader. So, I'm going to make a matrix4f variable. I'm going to put it. I'll put it at the end. Why? Yeah, I'll put it at the end. Why not? Okay, fine. I'll put it. Fine. I'll put it here. There. How about that? So we have the light matrix, and right here we're just going to set the light matrix to maltCamera.getViewProjection. That way we can, well, this way we can get the position, or the MVP, the model view and projection, just by multiplying this light matrix by the position in shader.cpp. So, in rendering to shader.cpp, speaking of, let's go ahead and, oh wait, first we need a way to access it. So let's first go to renderingengine.h, and let's make a way to access it. To do that, we can have an inline, matrix4f, get light matrix. And by the way, just the reason I'm calling it light matrix is because this is the, well, yeah, this matrix represents the way the world looks from the light's perspective. It represents the light camera, so that's why it's light matrix. And we're going to, of course, return light matrix. And there, that should be everything. So, in shader.cpp, let's add a way to access this. In update uniforms, under this sort of R subsection right here, I'm going to add an if check. I'm going to make it the very first one, in fact. And it's going to be if unprefixed name equals light matrix. So, if we're asking for the light matrix, then all I want to do is I want to set uniform matrix4f. I'm going to set, with the uniform name, I'm going to set it to that light matrix. So it's going to be rendering engine, it's a parameter, get light matrix, wherever you are. Yeah. And it's pretty much just going to be the same sort of way we calculated the projected matrix, except with the light matrix. So get light matrix times world matrix. There. And that should set the light matrix. I'll test one more time just to make sure I didn't break anything. Misspelled matrix here. Good job. Matrix. No. Matrix4f. And I think, nope. Alright, remember, that's a pointer type. And now I think we've done everything. Yeah. Everything we need to start writing the shadow map shit. Great. So, let's actually dive into the shaders. Let's just go ahead and open up all our lighting shaders. So like lighting.fsh. Don't need lighting.glh, I don't think. Lighting.vsh, lighting.main.fsh. Don't think we need that, but yeah. Sure, I'll just open all the lighting stuff. And let's actually implement something that reads from a shadow map. So, very first thing, I'm going to go to the vertex shader header for lighting. And I'm going to create, first off, I'm going to create a uniform for the uniform mat4 for that light matrix I created. So, R light matrix. And what I'm going to do is I'm going to create a varying variable. Actually I'll put it above TPN matrix. Varying vec4 shadow map chord 0. These are the these are the texture coordinates that we're going to be using to access the shadow map. Why making it a vec4 instead of a vec2? Well, you'll see right now, actually. The thing is, the way we access the shadow map is with the position that was used to generate it. Because if we go to the position that was used to generate it, that's going to be the exact pixel that has the depth information that we're after. So, and that's why we have, where is it? And that's why we're using that light matrix in the first place, because this is this matrix right here. This uniform and this uniform should have the exact same value. So, by that reasoning, all we should need to generate the shadow map coords is, well, the same thing we used in the shadow map generator, except with the light matrix, because TMVP means something different in this particular shader. And there, that should be the exact same position generated with shadow map generator. We can use that as coordinates to look up inside the shadow map. And that's pretty much the reason we're storing it as a vec4. Well, part of the reason. You could truncate it to a vec2, but it's not going to work, for reasons that you'll see very shortly. Now, since we do have a shadow map now, we're going to need to change our fragment shader header. It's going to need uniform sampler 2D for the shadow map. And this should already be... oh, wait. And it should actually be r underscore shadow map because it's part of the rendering engine. And that should be okay, I think. So, cool. We got the vertex shader, it's generating everything we need, and, oh, of course, the varying variable, we want to have a varying variable here for the for shadow map coordinates. And great! I think that's all we need in these two. We're generating the shadow map coordinates, we're passing them along to the fragment shader, the fragment shader's got a uniform to read the shadow map. All we need now is to actually access the shadow map in here. Why did OpenSampling.glh? You'll see in a moment. But first off, let's modify this a bit. Now right now we're setting the fragment color by, basically we're reading from the diffuse texture and we're multiplying that by the lighting effect. And that's nice, except, well, now the lighting effect's not necessarily going to be just this. Now we're going to sort of want to change this based on the shadow map coordinates, or the shadow map value. And you could, in theory, just add it on as a multiplication there, but I think it's getting a little bit unreadable there at this point. So let's create a vec3. I'm going to call it the lighting amount, and that's going to equal this. And, well, yeah, you don't need to do this at all. I just feel like doing this. My code organization sense is bothering me. And great. So I'm going to create one function in here, void, wait, it's going to be a float calc shadow map effect. And it's going to take in, I guess just a sampler 2D that I'll call the shadow map. And that's all we should need here. And of course, I'm going to multiply the lighting amount by however much the shadow map is affecting it. And actually, I'll just call it calc shadow amount. That's more accurate. Doesn't necessarily depend on, well, it does in this case, but you know, you get the idea. We're calculating the amount of shadow is at this pixel. We're just passing the shadow map, I think. So, great. And yeah, sure, I'll pass in vec4 shadow map coords. Again, you don't need to do this necessarily, since this is a function in here. It has access to it, but I want to make it less dependent on this particular set of, you know, uniforms and varying variables. And great. So with that, I think that's all we need to start writing the calc shadow map amount function. So how do we do it? Well, first off, we're going to need to convert this 4-dimensional set of coordinates to 3-dimensional set of coordinates. Why 3 and not 2? Well, again, you'll see it in a moment. So, I'll call these shadow map coords, I'll call these initial shadow map coords. How about that? just makes it a little bit more descriptive. And this is going to equal the initial shadow map coords .xyz divided by the w component. And this is perspective divide. And the reason we're doing this is because of one of the subtleties of OpenGL. When you set something in GL position and it's transferred to the fragment shader, it will automatically do, well, just this. It will take the XYZ coordinates of GL position and divide it by the W amount. And that's how it gets the final position. That's done implicitly in OpenGL, but since our shadow map coordinates aren't GL position, we have to do that manually. And the X and Y, shadow map coords.xy is the proper, position we need to sample to shadow map at, just so you know. Actually, there's one more subtlety to generating the shadow map coordinates. You see, when you perform a perspective divide like this, it'll give you coordinates in the range -1 to +1. And that's great, except texture coordinates need to be in the range of 0 to 1. So, we're going to need to do a little bit of transformation here. I'm going to put all that in parentheses. I'm going to multiply it by 0.5. That puts it in a range of -0.5 to +0.5. I'm going to add 0.5 to it. And that'll, of course, just put it in the range of 0 to 1. And that's great. So now our shadow map coordinates are completely valid, and we can use them to read our shadow map. So let's do it. Let's see what happens. I'm going to do texture 2D. I'm going to take in the shadow map, and for the chord, it's going to be shadow map coords.xy. And that'll give me a vec4, but shadow maps only have one, real value, so we want .r, which is the only value. And great, we read the shadow map. What does it give us? Well, this will give us how far the nearest pixel, how far the nearest object at this location is from the light. And well, that's not exactly what we're after. What we're really after when we read the shadow map is we want to know sort of a Boolean thing. Is this pixel in shadow? Yes or no? And, well, that's not what this is doing. Now, OpenGL actually has a function that will read a shadow map like that, but it's not universally supported, and where it is supported, sometimes the drivers are a bit buggy. For instance, on my drivers, if you try using that, then the shaders won't validate normally, and you have to do a certain hack to get your shaders to validate. So, yeah. At least right now, since it's not supported and since it's a little bit buggy in some places, I'd recommend just implementing the function yourself. It's not that hard, and that way you don't have to worry about any of the weird driver issues mucking things up. And that's why we have sampling.glh open. So I'm going to have a function that's going to return a float, and the float's going to be, of course, either 0 or 1, and it's going to be called sample shadow map. And the goal of that is to do, again, exactly that. It's going to return 0 if the pixel's in shadow, and 1 if the pixel is not in shadow. So, what's going to take in? It's going to take in sampler 2D for the shadow map. It's going to take in some vec2 for the coordinates, just like a normal sampling function, but it's also going to take in one more parameter. It's going to be a float that I'm going to call compare. And what this sort of compare is it's the distance that the pixel you're interested in is from the light. So we pass in how far. Where is it? Yeah, okay. Well, when we're using this function, we calculate how far whatever pixel we're looking at is from the light, and then we'd pass that in as the compare parameter. And of course, this would be in the range of 0 to 1, just like normal coordinates. And yeah, and that's why do we need that? Well, that's how we're going to determine it. If you remember the shadow mapping algorithm, you take the distance of the nearest object from the light. And basically, what we want to do is we want to know if this is less than the compare value. Because if this is... Wait, am I doing this backwards? Okay, I might have this slightly backwards, but essentially what we're doing is we're trying to see if the distance of the nearest object from the light is, well, if this is closer than the compare. Because if it is closer than the compare value, then that means, hey, there's some other object closer to the light, therefore it must be blocking the light from reaching this pixel, therefore it's in shadow, therefore return 0. Otherwise, return 1. And you might be wondering, hey Benny, how can you not care if your thing is correct? And the reason is we don't need to use conditional statements like this. OpenGL actually has a function that does exactly that sort of thing. It looks at two different values. If one value is, closer than 1, it returns... Yeah, if it's closer than the other, it returns 0. If it's further than 1. Exactly what I've just described. So I'm not going to be using if statements like this. I'm going to be using the step function. So that's what I'm going to return. I'm going to return step, starts with the compare parameter, and I'm going to look at, for the second parameter, I'm going to pass in, the distance of the nearest object from the light. And that's going to do just this. If this compare value, if the distance of what pixel we're interested in is farther away from the light than this is going to return 0. If it's closer or the same, this is going to return 1. And that's exactly what we want to do. And that's how you implement that sort of shadow sampling function yourself. There. It's not that hard. And now that we have it, we can use it. So, hopefully that made sense. I'm going to sample shadow map at shadow map. Now, of course, the coordinates are shadow map coords.xy. Oh, and in here, make sure that's coords.xy, because, that's what I named the variable here. Or, whatever your variable's named. And now for... And now for the compare value. How do we get that? Here's the interesting thing. If you think about it, you'll realize this is actually shadow map coords dot z. Because think about it for a moment. We're trying to find how far this pixel is from the light. And what we've essentially done is we've calculated the position relative to the light, right? That's what we did in our vertex shader with our light matrix and such. So, what shadow map's coords is this is the 3D position essentially of, this pixel from the light perspective. Therefore, the z, if this is a valid 3D coordinate, must be the distance from the light, because that's what all this thing is doing. It's a terrible explanation. Let's try that again. Take 2. Alright, so when you multiply a position by some MVP matrix like this, what you're doing is you're calculating the 3D position of it, essentially. You're doing the perspective projection, you're doing rotation, translation, scaling, all the different transformation to find its final position in 3D space, right? Right, of course. That's the whole basis of this, our whole basis of our 3D rendering system, essentially. So, this shadow map coord 0 holds the position of our vertex in 3D space, relative to the light, because the light's MVP matrix. Okay? So, once we do all the math to, finalize that with this right here, then the xy, that'll be its 3D position in the range of 0 to 1, and the z would be the 3D position in range, or the z position in range 0 to 1. So, that's why this is valid. Hopefully that makes sense. There. So now we got a sample shadow map function, has proper parameters, returning 0 or 1. So all we have to do now is return it. Now we should be able to build and run. And we crash. So clearly, I probably have some shader bug lying around somewhere. Probably made a typo or something, so one moment while I just find that off screen. And as it turns out, I just made a slight oversight. You see, in our forward ambient vertex shader, we were reusing lighting.vsh because they were the same. Now that we have shadow mapping, that's no longer the case. So I'm going to copy what was in lighting.vsh, and I'm going to get rid of the shadow mapping stuff. So now that should correct the error. And Yeah. Wait. And we don't need light matrix anymore. There. Now I should be able to run. And, oh, we still have one more error. Okay, I've made 3 small mistakes. First off, in lighting main, GLSL can't implicitly figure out whether this 0.5 should be, well, what size vector it should be. So I'm just going to explicitly cast it to a vec3. That way, everything works out as it should. The second thing is where I calculated light amount as a vec3, yeah, it's actually a vec4. So, yeah, make sure you fix that. The third thing is what sampling slot does our shadow map use? We never specified, so yeah, right here at the top of rendering engine, add new sampler slot for shadow map. I'm going to put it at 3. And if you build and run again, what's this? We have shadows, folks. And granted, the edges look not beautiful, but hey, we got shadow mapping working. So that's something. And great. But before I end this video, there's one small thing I want to do. I don't want to have to do this adjustment in the fragment shader, because there's actually a smarter way to do this. It doesn't matter too much right now, but you know, it's a nice thing and it's essentially free, so why not? What you want to do is, in the rendering engine, we're going to add a static const matrix 4f, and it's going to be called s_bias matrix. And all this is going to be is it's going to be a matrix that applies that exact same sort of 0.5 multiplication and transformation. So what we're going for is a matrix 4f that, well, it has 0.5 as the scale columns, and then 0.5 all down the translation column. Unfortunately, that's a little tricky since we don't have a, we don't have a constructor that lets you explicitly specify all individual components. So I'm going to use sort of a trick here to do that. I'm going to init scale to a vector 3f of 0.5, 0.5, and 0.5. And I'm going to multiply that, so that'll give me all the rows. I'm going to multiply that by init translation, and this is going to be 1.0. Why does that have to be 1.0? Because this is matrix multiplication. It's not just concatenating it, it's multiplying. And if you do it by 1.0, that will make it correct. I'll add a comment below to explain what this is doing, because that's definitely not explicitly clear, but hey, cool, we got a bias matrix, and private static const. Yes, that's the initialization. Well, clearly I've forgotten something here. So, yeah, one moment. And it's very, very simple. For some reason, I forgot to put matrix 4f here, and I'm not really sure why. And, const matrix 4f. There we go. And that should give me a proper bias matrix. And all we'd have to do to use this is include it in the light matrix. So where this is, just bias matrix times that. And now I should be able to build and run. And look at that, shadows are working just fine, just like before. Except now we don't have to do that transformation in the fragment shader. It's already done beforehand with the bias matrix. So cool, that's nice. Now, the obvious issue with this right now, of course, is the edges. They're very stair-steppy, the obvious aliasing going on here. And there's a few ways you can solve this. One way is just jack the resolution up, of course, make it higher resolution, fewer stair steps. And one interesting thing about shadow mapping is, since it is based on the same idea as ray tracing, if you could somehow have an infinitely large shadow map, all the different artifacts and nuances of performing shadow mapping that, you'd usually do at this point, would just go away, and your shadow maps would give you shadows that are identical to ray traced shadows. So, that's kind of interesting. Of course, we don't have infinitely large shadow maps, but still, just interesting fact, I think. But yeah. At this point, there's really two ways people like to go. One way is sort of just, okay, what can we do with this? What can we do to sort of just adjust the shadow mapping algorithm as it is, and just get better looking shadows with it. And that's what we're going to cover in the next video. Just the basic, how can we improve shadow mapping as it is, just to get better quality shadows without these stair-stepping issues, without some of the other issues that we haven't quite encountered just yet. And yeah. The other way is just to radically rethink the problem and do shadow maps completely differently. And that will make a lot of the issues go away. And, of course, it requires radically rethinking the whole thing, but it also makes things go away, and you don't have to deal with them. So, I don't know. There's two different ways to do it. We're going to cover the basic, how can we work with what we have, in the next video, and I'll cover the more radical idea in the video after that. And just so you know, the sort of working with what we have technique ends up with a shadow mapping technique called PCF shadows, and the radically rethinking thing ends up with a technique called variance shadow mapping. So, yeah. I think I've rambled on long enough. Now you've got basic shadow mapping working. And yeah, hope you enjoyed, hope you learned, and see you in the next video where we will be tackling some of the issues with shadow mapping and making our code, of course, a little bit better. Thank you. See you then.